The equilibrium constant is a unitless number that basically depicts where the equilibrium lies in a chemical reaction that goes in the forward and reverse directions. For the general equation, little a capital A plus little b capital B then turns into little c capital C plus little d capital D, and this goes in the reverse order as well. The capital A, B, C, and D are the chemical entities in the gas or aqueous phases. The small letters A, B, C, and D are the coefficients in the balanced chemical equation. K is a constant value and it's called the equilibrium constant. K is a different value for each different chemical system, and as well, at different temperatures for a particular chemical system, the K value will be different as well. That's why for most of the different problems you'll see in equilibrium, a temperature is always listed. That's because it's important to know what temperature the reaction's occurring at, because the K value for that particular temperature will be different than the K value for the same reaction at a different temperature. Let's consider the following chemical system. We have hydrogen gas and iodine gas, and it's being changed into hydrogen iodide gas. So that's the forward direction. But as well, the product, as written on the page, so when we talk about products and reactants, it's all to do with how it's written down. These are referred to as the reactants because they're listed to the left. This would be the product because it's listed on the right. But this product is still changing into reactant, and the reactant is changing into product when equilibrium is established. It's going both ways. So let's consider a few different experiments with different amounts of these entities. In the first experiment here, we have 2 moles of hydrogen gas, 2 moles of iodine gas, and 0 of the hydrogen iodine gas. That is left in a closed, sealed container. For equilibrium to be reached, the chemical system has to be in a closed system. Matter cannot be allowed to escape, or else equilibrium will never be reached. So a certain amount of time is elapsed, and then the concentrations of each of the entities at equilibrium are measured. So let's calculate the value of K for the first experiment. Well, we first need to write the equilibrium law equation. And if we go back up to the start, here it is. The equilibrium constant is equal to the concentration. Remember that square brackets refer to concentration. An amount per volume. In this case, we have moles per volume. Most of the units we'll be using in equilibrium are moles per liter for concentration. So we have the concentration of this product raised as an exponent to its coefficient. Then that's multiplied by the concentration of D product raised to its coefficient, there it is, and then divided by the reactant concentrations multiplied by each other, each raised to their coefficients. So it's important to remember that what K really is it's giving us an idea of the amount of product compared to the amount of reactant. And this is going to give us a ratio. So if you have a lot of product and very little reactant, well, you're going to have a K value that's greater than 1. Pretty high number. If you have a greater amount of reactant compared to product, well, your K value is going to be less than 1. So whether the K value is greater than 1 means something. It means it's product favored when equilibrium is established. At the natural equilibrium between the reactants and products, there's more product than reactant. If K is less than 1, then that means at equilibrium you have more reactant compared to product. And if K basically is pretty close to 1, it means you have relatively the same proportions of products and reactants. So let's calculate the equilibrium constant. K for this chemical system, and you're going to need the balanced chemical equation to be able to write this. It's our ratio of our product. In this case, we only have one product. State is going to be important. Don't leave that out. And we're going to square that because there's a 2,4 coefficient. And then we're going to divide that by our reactant concentrations. So we have the hydrogen gas raised to the 1 because there's a 1 for a coefficient. And we're going to multiply that by the concentration of the iodine gas. It is also going to be raised to the 1 because there's a 1 coefficient. So now I'm going to sub in the values. Whenever I do a substitution, I always replace my square brackets with round brackets. I make sure I write any of my exponents, and then I substitute in the proper amounts. So at equilibrium, K is always at equilibrium. So the hydrogen gas concentration is 0.442. The iodine gas is 0.442. And the hydrogen iodine is 3.116. All right, if you put all of this in your calculator, you will get a value of K of 49.7. Let's do the second one now. In this case, we're starting with 0% reactant. So no reactant. We're actually putting the product here into the closed vessel. We're going to give it time, and then at equilibrium, we have these concentrations. So let's now substitute in those values for our expression of K. So this time for the hydrogen iodine, we have 1.560, and I'm getting this, there's that value, that's where I took it from. For the hydrogen gas, we have 0.221, 0.221, and if you put that on your calculator, you get 49.8 as the ratio. Let's now do the third one. So this time, we have no hydrogen gas. We have some amount of iodine gas, and we have some amount of hydrogen iodine. So this is put in the closed vessel, it's given time to establish equilibrium, and then at equilibrium, these are now the concentrations. Bear with me, it's a little hard to write on this at times. Sub that into your calculator, press equals, and you get 49.8. All three of these values are basically the same number. If you were to round them up to 2 sig figs, they'd be 50. 50, 50, 50. It doesn't matter what amounts you start with. It doesn't matter if you only have reactant, or you only have product, or you have some product and reactant. Once equilibrium is established, this natural place for this particular chemical reaction at the temperature it's reacting at, the ratio of the products to the reactants always gives you the same ratio. That is why this is called a constant. It's a constant number.